Have we ever heard of even and odd functions before?
Nope.
Not really. Okay. So even functions, similar to like a y equals x squared. Okay, it's going to be reflected across the y-axis. So if I know this is an even function, number 7 for example here, if I know that is an even function, the other part of it, all of my negative x's are going to have the same output as my positive x's. So everything that's over here is going to get reflected over here as well. And so we'll be able to see that all of these points get reflected across the y-axis. And so as we take this and we try to form out our shape here, we'll see that our graph should look symmetrical across the y-axis. Okay? Similar with number 8, all you're doing is taking all of your negative x's and giving the same output to your positive x's. And this way we end up with things that are reflected across the y-axis. Okay, so we'll end up with stuff that looks kind of like that. Okay, so those are even functions. What if I wanted to do so algebraically? Okay, so if it was graphically, we're looking across the y-axis, and so we'll end up with things that look reflected like that. However, if we want to see it algebraically, we're going to do a similar situation. So we're saying anything that had a negative x is going to have the same output as a positive x. So we're going to see, is this always true? So we're going to plug in some constant, some generic constant we're going to call k for the moment. And we'll do something like this where f of x is this equation. And so I will plug in negative 7 times the absolute value of our negative value, so negative k, plus 3 times our negative k squared, plus 5. I want to know, does all of my negative x's go to the same destination as all of my positive x's? All right, so what's going to end up happening here is if this is an even function, all of the negative inputs should have the exact same output as the positive inputs of that value. Okay? So we'll simplify this. Negative 7 times the absolute value of k is negative 7 times k, plus 3 times negative 1 squared is positive 1. So this is plus a 3k squared, plus 5 equals negative 7 times absolute value of positive k is still positive k, plus 3k squared, plus 5. Are those the same equations? Yes. So when these match up, this is an even function. If they don't match up, then it's an odd function. So for example, if we were looking at number 10, okay, number 10, we have 2 times our negative input to the 4th power minus 6 times our negative input plus 1. Is this going to be equal to the positive input? Guys. Okay, so 2 times our k to the 4th minus 6k plus 1. Okay, so as we go by and simplify the left side here, you've got negative 1 to the 4th is positive 1. So this is 2 times k to the 4th. Minus 6 times negative k, this becomes a plus 6k. Plus 1 equals 2k to the 4th minus 6k. Is this the same equation? No, these ones are different. So this is not an even function. I'm not sure if it's an odd function or neither yet, but I know for sure it's not an even function. Okay? So that's how we can test algebraically if something is an even function. Similarly, we're going to take a look at how we can test things that are odd functions. Okay, so graphically with an odd function, what we're talking about is stuff that is symmetrical across the origin. So in other words, what we're looking at is every x comma y coordinate point I have, there's going to also be a negative x, negative y. So for example, this coordinate point here is at 0, negative 2, so 0, positive 2 is going to exist. This coordinate point would be negative 2, negative 5, so positive 2, positive 5 will exist, and so on. So we can reflect all of these coordinate points. And so we'll see that when we reflect this across the origin, we end up seeing something that'll look like that. So visually, we're reflecting across the origin now. Or in other words, you're taking every x, y coordinate point, making it into negative x, negative y. Similar over here, you'd end up with something that looks kind of like this. So a curve. Okay, and so we could have a visual thing that looks like that. Questions on visual odds? Are we doing okay? So just like we did with evens, we can also check this algebraically. And so we're going to see R or is a given equation an odd function? If it holds true, then yes. If it does not hold true, then no. In this case, we're going to know, do all of our xy's go to negative x, negative y's? So do all of my negative x's go to a negative y? Is essentially what we're asking here. And so when I plug in something, we'll do number 16 here as an example. So is 1/2 times our negative k cubed minus 6 times negative k. Is that function the same as negative times the entire thing? So a negative y. Oops, this is not x, this will be k. Okay. So in this case, negative k to the third, negative 1 to the third is, Jacob? Good, negative 1, so this becomes a negative 1/2 k cubed. Okay, minus 6 times negative k, this becomes a plus 6k. Equals, okay, and then we'll distribute that negative to both parts. This becomes negative 1/2 k cubed plus 6k. Are those the same? Yes, so this is an odd function. If they did not equal the same thing, then we would know it's not an odd function. Okay? Kind of makes sense? Huh? Because I'm testing if it's odd. So right now I want to know, do all of my negative x's go to a negative y? I wanted to test for an even function. Great question, because that's coming up next. We're going to take a function and determine if it's either odd or even or none of the above. And so given this one, okay, I want to know, is it even or is it odd or is it neither? Okay, which one do you guys want to do, 19 or 20? 19. Okay, weird because it's on your homework, huh? All right, so if I want to check to see if it's even, I'm going to see, does every negative x have the same output as every positive x? So we're going to plug in, is negative k cubed minus negative k squared, is that the same as positive k cubed minus positive k squared? And as we distribute, or as we apply these exponents to simplify, negative 1 cubed is negative 1, so this is negative k cubed, minus negative 1 squared is positive 1, so minus k squared, equals, this is already simplified. Are these the same equation?
Yes.
Are those the same equation? No. So this negative out front is what's making this difference. So those are not the same, so this is not an even function. Then we can say, is it an odd function? Okay, so now to check if it's an odd function, we want to know, does every negative x go to a negative y? So you already found negative x. This is our negative x. So is negative k cubed minus k squared the same as the negative y? So negative times our quantity k cubed minus k squared. As we apply that negative to both parts, we see that it will equal negative k cubed plus k squared. So are these the same? No, so this is not odd either. So in this case, it is neither odd or even. Okay? If one of these were to match up, then we would be able to identify it as odd or even. Every once in a while, you get one that works in both cases. So let's say like a circle, for example. A circle is both reflected across the y-axis and across the origin. So that could be both even and odd. And just like in this case, a lot of times we'll see equations line up where it's neither even or odd. All right. Questions on the even and odd, because we're going to start to shift into a slightly different mindset now. Are we okay with even and odd? For the most part, even, you reflect across the y-axis, so you're checking, do all my negative inputs go to the same output as the positives? And then if it's odd, it's reflected across the origin, do all my xy's go to a negative x, negative y? Next thing we're going to start doing is looking at graphs and identifying kind of what's going on with them. And so for like things like number 25, we're going to ask, given this graph, use this graph to help solve the inequalities indicated. So I'm going to give you some function of x, and you're going to tell me when f of x is greater than or equal to 0. We haven't quite taught you yet how to find the 0, so we're just going to give you the picture. And so what you'll see is, there's our 0 points. Those are important. When is this function greater than or equal to those points? Well, it's greater than in that spot, and it's greater than in that spot. So using interval notation, here comes back the interval notation. I think about 137 of you taking the test, and I give you the option to not use interval notation. I think only 5 of you, maybe 6 of you actually used it. So we're going to try to come back to it. So we can say that, in this case, f of x is greater than or equal to 0 when x is between negative 1 and 1. So square brackets because of the equality, negative 1 to positive 1. Unioned with, because I have more options, anytime I'm greater than 3. So we'll include 3 as an endpoint, since there's equality still. And then they'll go off all the way into infinity, which is always a rounded bracket. Okay, so we'll have those two intervals is when f of x is greater than or equal to 0. Okay? So you'll have to look at the pictures given to you and solve the inequality. Some of them will be less than, some will be less than or equal to, and use your proper interval notation for this. Next piece is going to be looking at graphs and identifying when things are increasing and decreasing. Okay, so we're going to again use interval notation here. But now we want to know when are these increasing, decreasing, or constant right answers using interval notation. Assume all endpoints have integer values. So we'll be able to look at these endpoints. So there's an endpoint where things will change. There's an endpoint where things will change. And there's an endpoint. The most important thing, I think, with looking at if it's increasing or decreasing is, remember, you have to always read it from left to right. So as our x increases, as we head left to right, I'm increasing when y values are increasing. Okay? And I'm decreasing when y values are decreasing. So as I read this from left to right, am I increasing or decreasing at the beginning here? So x is increasing, x will always increase. Is y going up or down? Y is going down. Even though that arrow wants to fool us, okay, we're not going up over here. We're actually decreasing as we come from this direction all the way until we hit this x equals 3 value. So I'm decreasing when x is any of these numbers, because that arrow tells us it goes on for forever. So from our negative infinity of x's all the way up until that point at 3, negative 3. Okay. And so we're decreasing at that point. Okay. Another spot where we're decreasing is between these two purple dots. So from 1 to 4. So this would be unioned with 1 to 4. Okay. Then I could talk about I'm increasing. Okay, so these would be our decreasing moments forever in this piece. Our increasing moments we could look at. Let's use green for that. We're increasing here and here. And that has an endpoint on it, not an arrow. So we have x as an element from -3 up to +1. And the other thing I think that's difficult is we're only looking at the x values, so you don't have to necessarily know what y is at the moment, just what's happening to y as our x is changed. And then this is going to be unioned with from 4 to our endpoint stops at 6. So 6, and that endpoint is included because it's a solid circle. Okay, so that was where we were increasing. Okay, just stop. Any questions on the increasing, decreasing piece? Yes, Henry?
You don't need to worry about the y values.
We don't necessarily need to worry about the y values. I just want to know when this graph is behaving certain ways. The only time we're going to really worry about the y value is for like maximums.
Okay, you look fine.
Okay. So let's take a look at something that'll piece it all together for us then. Is the one? Oh, no, that's not the one. Hold on, I got one weird. Okay, so eventually what we're going to be able to do is you're going to be given some model, and you'll be able to tell me pretty much everything we'd ever hope to know about it. Okay, so in a real life situation, let's think about this maybe as like a profit equation for a company. You're going to be able to tell me what the domain and range is, so we can look at the realistic domains and range. You're going to be able to identify where the zeros are. So again, if it's a profit situation, you can tell me where the break-even points are. Where the function is greater than 0, when it's less than 0. So when am I making money, when am I losing money? Where it's increasing, where it's decreasing. So where are we becoming more profitable? When are we becoming less profitable? And then finding local max and min. So when do I maximize my profit? So we can tell all this stuff from it. So we'll look at number 41. First piece is find your domain and range. So domain is all of our x values. So our domain in this case, we're looking at 41. We have arrows on both those. Means it's going forever. What's my domain? Infinities, right? It's from negative infinity to positive infinity, which we can just simplify as all real numbers. Okay? Or you could write it as your negative infinity to positive infinity. Either is acceptable. Okay? So in a theoretical world, we can go anywhere we want. Our range, okay, so our y values, now y is important. What y values, what are my outputs? Dylan?
Everything less than 5.
Excellent. So 5 is my max here. Everything below it, we've got arrows. So I can say from negative infinity all the way up to and including positive 5. Okay? So there's our domain. Domain and range is identified. We can go find the zeros. Okay? So our zeros of the function. Okay? I want to know when is our y value 0. So they have that identified. It's when x equals 1 or 3. Okay? There's our 2 zeros of the function identified. We'll be able to go find those later on in the year by hand, but right now we'll just look at the pictures. Okay, where's the function greater than or equal to 0? So when is our f of x greater than or equal to 0? It would be when our x is in this area above it. Okay, so we're looking for greater than or equal to, so we'll have square brackets from 1 till 3. When is it less than or equal to 0? Okay, so now we're going to look at when is it below our 0. This will be all of our other x's, so all of this stuff. So we've got negative infinity up to 1, which again, they're using equality, so we'll have square brackets. Unioned with 3 to positive infinity. And then we'll talk about increasing and decreasing. So now as we switch our mindset into increasing, decreasing, we'll see that it's increasing in this first half. Okay? And so we'll see that our x values, so this is our increasing area, is going to be from negative infinity all the way up to that max point, which is at 2. So our x value is 2, that's the important one. So we're increasing, 4 being constant, so we'll include that point, it's fine. And then the decreasing piece is going to be that part as we're going down. So we'll decrease when x is greater than or equal to, I guess we'll keep the square brackets. Okay, so now we have the increase and decrease. Last piece is going to be identifying the max or the min. In this case, it's a local maximum. So at the very top, that point, my maximum is the coordinate point 2, 5. Okay. Now we have a ton of information about this graph. We've decoded it. We know exactly what's going on. Anyone who asks us a question about when we're being profitable or stuff like that, we've got all that stuff decoded. We know what's going on. Okay. So for the most part, what we're doing is we're just looking at graphs and we're telling people what's going on with them. And then lastly, we will take some equation that's not very friendly and let our calculator do all the work for us. Okay. So every once in a while it's nice to find maximums and minimums to stuff, but us doing the calculations on it is very tedious and time consuming. And so what we'll do is we'll just take this piece and plug it into the calculator, let the calculator do the work for us. So if we look at number 49, you want to take this, plug it into your y equals equation. And so I'm going to pull up the calculator real quick. Okay, so we'll take that equation, we'll plug it into our y equals. Once it's typed into our y equals, we can then go to our graph, That was nice of them to keep it in our 10 by 10 window. And then you can have the calculator do the work and find the max and min. So if you go second trace, it's going to calculate stuff for us. You can go find your maximum value, which is the fourth option. It'll ask you 3 questions. Left bound, right bound, and a guess. So go left of our maximum. Go to the right of the maximum. So you set your left and right bounds because there could be multiple maximums. You want to find that local maximum. And then a guess, somewhere in the middle. Then the calculator will spit it out to you into the nearest hundredth, which I believe is what it asked. You can say my maximum is at 0.78, comma 1.58. Similarly, you can go to second trace, calculate your minimum, the third option. And again, we can set the left bound. Set the right bound, so go to the left and right of your minimums. Guess, you can pick somewhere in the middle. Let the calculator do the work for you. So my minimum is at 2.55, comma negative 0.47. And then we have what we're looking for there. Okay, so you have your max and mins. Last thing I want to talk about is just when it's talking about local max and minimums, you want to look at the idea that it's just the peaks and valleys of your graph. We're not going to include the endpoints. Obviously, theoretically, my maximum is infinities, but we want to look at just local max and mins. So you're only going to look at the peaks and valleys. So the green ones would be maximums, the red ones would be mins.